Hi and welcome to John's Maths Book. In this video, we'll be exploring another key concept in mathematics. If you find this tutorial helpful, then please show your support by subscribing, liking, and leaving a comment. Your positive engagement helps me create more content and allows me to bring you more valuable maths lessons. Without further ado, let's go over to the whiteboard. In this exercise, we have a right circular cone with its base on the xy plane at z equals 0. The equation of the cone is z equals 2 minus the square root of x squared plus y squared. The cone is cut by a plane parallel to its symmetrical axis. The plane cuts the y-axis at y equals 1. Our task is to find the volume of the section of cone that remains using double integrals and polar coordinates. Let's first take a look at the shape in 3 dimensions. First up, here's the complete cone. Its circular base sits directly on top of the xy plane. The circular base has a radius of 2 and is centered at the origin. If the cone is now cut by a plane parallel to the z-axis, or axis of symmetry, shown here in red, we see that a section of cone is removed. We'd like to find the volume under the section of cone that remains. Our first step in calculating the enclosed volume is to find the area of the region of intersection between what remains of the cone and the xy plane, where z equals 0. And to do this, we'll use polar coordinates. Let's first define the circular region at the base of the cone. We can do this by equating the equation of the cone, so z equals 2 minus the square root of x squared plus y squared, with the xy plane, so z equals 0. We have both equations in terms of z, so we can equate the two. Equating the two equations gives 2 minus the square root of x squared plus y squared is equal to 0. And rearranging this gives the square root of x squared plus y squared is equal to 2. And squaring both sides of this equation gives x squared plus y squared is equal to 4. Sketching the region in the xy plane, we see it's a circle centered at the origin with a radius of 2. Now, the line defined by y equals 1 cuts this circle, removing a segment. We need to find the area of the remaining region. To do this, we'll convert the circle given by x squared plus y squared equals 4 and the line given by y equals 1 to polar coordinates. Beginning with the circle, to convert from Cartesian to polar coordinates, we need to replace x with r cos theta and y with r sin theta. So in Cartesian form, the circle is x squared plus y squared is equal to 4. Making the substitution for x and y, we have r squared into the bracket of cos squared theta plus sin squared theta is equal to 4. And using the trig identity where cos squared theta plus sin squared theta is equal to 1, we have r squared is equal to 4. And taking the positive square root of both sides of the equation, we have r is equal to 2. And for y equals 1, making the substitution for y, we have r sin theta is equal to 1, which leaves r is equal to 1 divided by sin theta. Now let's look at what we need to do to find the volume. The volume is a double integral over the region capital R. This will sum infinitesimally small pieces of area, shown here as dA. When we multiply the infinitesimally small pieces of area by a height function, shown here as f of xy, this will give infinitesimally small pieces of volume. Now let's look at what happens when we sum or integrate from the origin of the circle to its perimeter and from the origin of the circle to the horizontal line. This will give us a better understanding of our inner integrals. When we integrate in the r direction, this will represent the inner of the integrals. This diagram represents a sector of the region capital R. The angle it makes is infinitesimally small and is denoted by d theta. Within the sector, we have infinitesimally small pieces of area denoted by dA. The size of each area is the length multiplied by the width. So in this case, dr is the length and r d theta the width. So dA is equal to r dr d theta. To find the total area of the sector, we integrate or sum in the r direction. So when we sum or integrate in the r direction, for this exercise, we begin at the origin of the circle, so where r is equal to 0. And we first travel to the boundary of the circle, so where r is equal to 2. When the circle intersects with the horizontal line for the first time, we travel from r equals 0 to r equals 1 divided by sine theta. This continues until the horizontal line intersects with the circle for the second time, at which point we travel from the origin where r is equal to 0, once again to the boundary of the circle where r is equal to 2. If we multiply an infinitesimally small piece of area, dA, by a height function, we get an infinitesimally small piece of volume, dV. So that's the height function, f of xy, multiplied by r dr d theta, which, as we saw, is an infinitesimally small piece of area. We can now define the limits of integration of the inner integrals. In each of the three cases we looked at, we saw that we began at the origin of the circle, so where r is equal to 0. In the first case, we saw that we began at r equals 0 and we ended at r equals 2, where the circle intersected with the horizontal line. In the second case, we saw that we began at the origin of the circle where r is equal to 0, and we continued along the horizontal line until it met the circle for the second time. So that was when r was equal to 1 divided by sine theta. And in the third case, we saw that we began at the origin where r is equal to 0, and we traveled to the perimeter of the circle, so where r was equal to 2. And in each of these cases, we were summing infinitesimally small pieces of area dA, which equated to r dr d theta. I'll deal with the height function f of xy shortly, but let's first find the limits of the outer integrals. So that's when r rotates about the angles of theta. As r rotates in a counterclockwise direction from theta equals 0 to theta equals 2 pi, theta being the angle r makes with the x-axis, the radial distance from the origin is first determined by the circle. When the circle intersects with the horizontal line for the first time at some angle of theta, the radial distance from the origin is determined by the horizontal line until it once again intersects with the circle at some angle of theta. At this point, and until theta reaches 2 pi, the circle is used to determine the radial distance r. At theta equals 2 pi, the area is complete. To determine the angles at which the circle and the horizontal line intersect, we can equate the two polar equations. So we have the equations r equals 2 and r equals 1 divided by sine theta. Equating the two gives 2 equals 1 divided by sine theta. So this leaves the sine of theta is equal to a half. And starting at 0 and moving towards 2 pi, the first time the sine of theta is equal to a half is at theta equals pi by 6. And this is the first point of intersection between the circle and the horizontal line. The second occurrence occurs where theta equals 5 pi by 6 and is where the circle meets the horizontal line for the second time as we move counterclockwise from 0 to 2 pi. Now we understand the region as we rotate about theta, we can define the limits of integration of the outer integrals. In the first of our outer integrals, theta begins at 0 and travels to where the circle meets the horizontal line. So that's where theta equals pi by 6. The second of the outer integrals begins where the circle meets the horizontal line for the first time. So that's where theta is equal to pi by 6. It then ends where the circle meets the horizontal line for the second time. So that's where theta is equal to 5 pi by 6. And the third of the outer integrals begins where theta is equal to 5 pi by 6, so where the horizontal line meets the circle for the second time, and continues to where theta equals 2 pi, and where the area is complete. Now let's deal with the height component, f of xy. We have two functions representing the cone and the xy plane, between which we are calculating volume. We need to subtract one function from the other to determine the height component. To facilitate this, we need to assess which of the two is larger when x and y are 0. So which is the top function and which is the bottom function? And in this case, it should be fairly intuitive. If we take the function of the cone, which is z equals 2 minus the square root of x squared plus y squared, and substitute 0 for x and y, we get z equals 2. So for the xy plane, we simply have z equals 0. So in this case, the top function is the function of the cone. So that's z equals 2 minus the square root of x squared plus y squared. So now we need to convert this function to polar coordinates. And to do that, we substitute our cos theta for x and our sine theta for y. And making this substitution, we get 2 minus the square root of r squared into the bracket of cos squared theta plus sine squared theta. And using the trig identity where cos squared theta plus sine squared theta is equal to 1, we have 2 minus the square root of r squared. And taking the positive square root of r squared, we're left with our height function of 2 minus r. Now that we have formulated all three double integrals, we can begin the evaluation process. Starting with the first of the inner integrals, we have the integral from r equals 0 to r equals 2 of r into the bracket of 2 minus r dr. Using the power rule to evaluate this, its antiderivative is r squared minus r cubed divided by 3, and we need to evaluate it between 0 and 2. And plugging in the values for r equals 2 yields 4 minus 8 divided by 3, and when r is equal to 0, it yields 0. So 4 minus 8 divided by 3 gives 4 divided by 3. And now working on its outer integral, we need to integrate between theta equals 0 and theta equals pi by 6, 4/3 d theta. And using the power rule to evaluate this, its antiderivative is 4/3 theta, and we need to evaluate between theta equals 0 and theta equals pi by 6. Now if we plug in theta equals pi by 6, this yields 4 pi by 18, and when theta equals 0, this resolves to 0. So this double integral resolves to 4 pi by 18. I'll leave the middle of the three double integrals until last, as it's the most complex of the three. So next, I'll move on to the third of the three. Evaluating its inner integral, we have the integral from r equals 0 to r equals 2 of r into the bracket of 2 minus r dr. Using the power rule to evaluate this, its antiderivative is r squared minus r cubed divided by 3, which we need to evaluate between r equals 0 and r equals 2. And plugging in the value for r equals 2 yields 4 minus 8 divided by 3. And plugging in the value for r equals 0 yields 0. So this integral evaluates to 4/3. And now working on its outer integral, we need to integrate between theta equals 5 pi by 6 and theta equals 2 pi, 4/3 d theta. And using the power rule to evaluate this, its antiderivative is 4/3 theta, and we need to evaluate this between 5 pi by 6 and 2 pi. Plugging in the value of theta equals 2 pi yields 8 pi by 3, and when theta equals 5 pi by 6, we get 20 pi by 18. And so 8 pi by 3 minus 20 pi by 18 is equal to 28 pi by 18. And now moving on to the middle of the three double integrals, we want to integrate between r is equal to 0 and r is equal to 1 divided by sine theta of r into the bracket of 2 minus r dr. And using the power rule to evaluate this, its antiderivative is r squared minus r cubed divided by 3. And we need to evaluate this between r equals 0 and r equals 1 divided by sine theta. Plugging in the value for r equals 1 divided by sine theta yields 1 divided by sine squared theta minus 1 divided by 3 multiplied by sine cubed theta. And plugging in the value for r equals 0 yields 0. And now moving on to the outer integrals, we need to integrate between theta equals pi by 6 and theta equals 5 pi by 6 of 1 over sine squared theta d theta minus the integral between theta equals pi by 6 and theta equals 5 pi by 6 of 1 over 3 multiplied by sine cubed theta d theta. And starting with the first of these, the integral of 1 over sine squared theta d theta is minus 1 over tan theta, and we need to evaluate this between pi by 6 and 5 pi by 6, and this yields a result of 2 multiplied by the square root of 3. If you'd like to know how to integrate 1 over sine squared theta d theta, please see this video. And for the second integral, we need to integrate between pi by 6 and 5 pi by 6 minus 1 divided by 3 sine cubed theta d theta. The antiderivative of this is 1/6 into the bracket of cos theta divided by sine squared theta minus the log of the mod of tan theta over 2. And we need to evaluate this between pi by 6 and 5 pi by 6. And if we plug in those values for theta, this yields minus the log of 2 plus the square root of 3 minus 2 root 3 divided by 3. That's all the integrals evaluated, and that's all that remains is to add up the constituent parts. So our final result is 16 pi divided by 9 plus 4 root 3 divided by 3 minus the log of 2 plus root 3.